Hi everyone. So what I'm going to be covering today is a thing called the binomial distribution. And this is basically a specific situation where we have basically a few things. We have a set number of trials. Well, first of all, before I do that, I'm going to write down binomial distribution criteria. So that's the main thing. We're looking at the criteria for us to be looking at a binomial distribution. It is essentially defined as a set amount of attempts at a certain event. And if that event happens, it is a success, and I can try it a bunch of times. So an example is me trying to kick a ball into a goal. I could try that 20 times, and I might make 5 of them. I could make 10 of them. I could make 3 of them. So there's a set number of attempts, which is 20, and then there could be an amount of successes. So that's the main thing. We have attempts at making an event happen, which we're going to call N, and we're going to have successes, which we're going to call R. Now what we also have is the probability of any single success. It's going to be P. So, for example, let's think about it like this. In a soccer penalty, there is a 1 in 5 chance I will score a goal. It's like in any single soccer penalty, any penalty shot, which is when you put the ball down and you kick it and try to get into the goal, in any single attempt at a penalty shot, there is a 1 in 5 chance. In a soccer penalty, now I said, if I tried to take 5 penalties, what is the chance that I make 3 of the shots? So that means out of the 5 penalties I take, what is the chance I score 3 of them? Now this is going to serve as like our investigation of how binomial distribution works, and we're going to derive a bit of a formula for this. So conventionally, with the current knowledge you probably have now, and from my previous videos, I want to move this to another page just so I can feel more working. Paste all that. Okay. We would conventionally draw a tree diagram. There's a chance I score, there's a chance I don't score. The chance of me scoring any single attempt is 1 in 5. The chance of me not scoring is 4 in 5. That's the first. This here is the first attempt. Then there's the second attempt. And there's the third attempt. Fourth attempt. Fifth attempt. And this is going to just get more and more complicated, as you can see. Now I'm not even going to bother writing them all out. Just a few of the important ones. So 1, 2, 3. But as you can see, it's quite a lot. And this can get quite confusing quite quickly. And that is why the binomial is basically going to be a shortcut to display how that works. Whoa, okay, I need to bump that down a bit to fit that. Let's make this one bigger. As you can see, quite a lot is going on. And if we think about it, there's quite a bit. So if I just move all of this in, for each individual attempt, so if we were here, the chance of us scoring here in our second attempt is still 1/5 because it's an independent attempt. We're just having another attempt at it. Same thing, 4/5 here. Similarly, chance of this here, 1/5, 4/5, 1/5, 4/5, so on and so forth. You get the idea. Similarly, 1/5, 4/5, 1/5, 4/5, so on. It goes on for ages. So as you can see, a lot going on here. Big tree diagram. Now I said, what's the chance that I make 3 of the shots? That means that I need to figure out all the combinations, all the different ways I can make 3 shots. Like, I could go 3 shots here and then miss 2 shots. That's one way. I could go make 2 shots, miss 1 shot, score a shot, and then miss 1. Or I could go 2 shots, miss 2, and then score 1. So a lot of different combinations. But if we think about it, let's just go through one path. Let's say we went score, 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 didn't score, didn't score. The probability of this precise order happening, where there's still 3 goals out of the 5 attempts, because we score 3 and we miss 2, is going to be the 5th probability of the score times the 5th probability of the score times the 5th times the 4/5 times the 4/5. Because it's 1/5 for each of these 3 scores and then 4/5 for the 2 misses. Similarly, now let's think about this. Probability of score, score, miss, score, miss. The probability of a score is 1/5 times the probability of the second score, 1/5, times the probability of a miss, which is 4/5, times the probability of another score, which is 1/5, times the probability of another score, which is 4/5. And we can rearrange that. So if I just put this on this side and then this on this side, just swap the positions, which you're allowed to do for multiplication. You're allowed to just move them around if it's all multiplication going on. You see it's 1/5 times 1/5 times 1/5 times 4/5 times 4/5, which you may observe is the exact same thing as this. So this is one possibility, and this is another possibility. So if we wanted the overall probability of scoring 3 goals, we would have to get the probability of this situation, add it to the possibility of this situation, plus all the subsequent possibilities. But as you may observe, what ultimately happens is it's the probability of 3 scores and 2 misses. Because there are 5 attempts. If I said what's the probability of 3 scoring, that means I have to miss 2. Now we know the probability of any single score is 1/5. And we are timesing that by the amount of times that we score. Now, if one single score is 1/5, the probability of 3 scores is going to be 1/5 times 1/5 times 1/5 3 times, as we can see over here, or over here. So it's ultimately going to be 1/5 cubed times the probability of missing times to the power of the amount of times I do miss. Now we can see here, we miss twice, so it's going to be 4/5. All that squared. Now all that's going to be multiplied by the amount of different ways, the combinations. So like, it could be score, 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 miss, miss. It could be score, score, miss, score, 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 miss. It could be score, miss, miss, score, score. All the different combinations times the amount of combinations. Because the probability of 3 scores and 2 misses, or the probability of scoring 3 out of 5, this will factor in all of this formula here. No, that's not the best explanation. Should I not even bother deriving it? Should I just give them the formula and then just be like, on your way? A bit slack in it. Not a Pascal's triangle. That's not good. That's not a good idea. Sorry, I'm just thinking out loud. Okay. So as we can see, the probability of 3 scoring is 1/5 cubed, and then the probability of missing 2 is 4/5 squared. Because we can see that in each of these situations, this involves 3 scoring, 3 scoring, and then this one also involves 3 scoring. And basically in every other combination, it would also have a combination, a version of 3 scoring and 2 missing. It'd just be the order that is different. So if each of these probabilities is the same, and all the subsequent ones will all be the same, then we can add them up, and it's just going to be the number of those times any single one of them, because it's like repeated addition. So this is basically the formula. The probability of scoring 3 goals out of 5 is going to be the probability of scoring 1 to the power of the amount of times we actually do want to score, multiplying that by the probability of missing the remaining amount of times. So the probability of missing once to the power of the amount of times that are remaining that we have to miss to ensure that we only score 3 goals. And we're multiplying that by the number of combinations. Now this is going to lead to a thing called combinatorics. Combinations. And that's going to lead me to this formula here called NCR. Now what this basically says is, with n attempts, how many times do I have R successes? What are the different combinations that can happen? What are the amount of different ways that can happen? So in terms of a formula, you just need to remember it's n factorial all over R factorial n minus R factorial. Now let's go through an example for that, and I'll sort of explain what factorial is when I actually get to some numbers. So if we go back to this example over here, which is saying that we have 5 attempts and we have to make 3, we are ultimately going to be finding 5C3. So this is saying the number of ways we can have R successes with n attempts. So I'll reiterate, n is the number of attempts, R is the number of successes. And this is basically going to overall give us the amount of different ways we can have that specific outcome of having 3 successes in 5 attempts. So 5C3 is going to be, if we plug it all in, we have NCR here. It's going to be 5 factorial, because 5 is n in this case, all over 3 factorial times 5 minus 3, because n minus r, all factorial. Now, let's rewrite that. It's 5 factorial over 3 factorial. Now, 5 minus 3 is 2, so that's going to be 2 factorial. Now, factorial basically just means it's going to be 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. So factorial is basically saying you just times by every previous whole number until we get to the very last one. That's pretty much it. So that's going to be 5 times 4 times 3 times 2 times 1, all over 3 times 2 times 1 for the first one, or 3 factorial. And then 2 factorial is 2 times 1. And you can just put that in your calculator. You can also put in this in your calculator, which I'll get to soon. I'll get to that a bit later on. But right now, if we just did that by hand, right, 20 times 6 is 120. Over 6 times 2, which is 12, you're going to get 10. So what we know then is from this, we know that there are 10 combinations for having 3 successes in 5 attempts. So there are 10 possible ways. There are 10 possible branches that would result in 3 successes and 2 misses out of 5 attempts. So now that we know that, we can go back to our formula where we said that the probability of 3 scores and 2 misses is going to be this times the combinations, which we said was 10. Fifth to the power 3, 4/5 to the power 2, times, we said the combinations, which is 10. And that would ultimately result in our overall probability in the events happening. Now let's sort of try to broaden this out. That means in a binomial situation, we've observed that this situation that I've given you only has really, in any single attempt, there's only two outcomes, a success or a failure. Score or not score. Success or failure. That's the main thing. In a binomial situation, the probability that x equals r, so this means we have r successes, the probability of having r successes is going to equal the probability of any single attempt. So let's say that if p is the probability of any single success happening, the probability that x equals r, the probability of r successes happening is going to be the probability to the power of r. So similarly, let's look at this. This is saying we have 3 successes. This is the probability of any single success. So the probability of 3 successes is going to be the probability of 1 success to the power of the amount of actual successes we need overall. Then it's going to be times by the probability of failure to the power of the amount of remaining attempts that need to fail. So if we think about it like this, if I have 5 attempts and I need to score 3, and I only want to see the probability of scoring 3, that means I have to miss 2. I have to. Otherwise, it won't be 3 scores. If I miss 3, then I've only scored 2. If I've missed 1, I've scored 5. If I've missed 1, I've scored 4. So as we can see, we need to also account that if we have n attempts, this is going to be the probability of a failure, which is the same thing as 1 minus p. Please take note of that. As we can see, the probability of succeeding is 1/5, so we said, okay, 4/5 is a failure. So to work out a failure, it's going to be 1 minus p. And that's going to be to the power of the remaining attempts that are left. So if we think about it in this context, if I've scored 3, I only have 2 attempts left, I have to fail those. So that's the amount that's left. And we worked out 2 because overall there are 5 attempts, so then it would be 5 minus 3 would be 2. So the total number of attempts minus the total successes we need. So the amount of failures would be the probability of any single failure to the power of n minus r, because n is the total amount, r is going to be the amount of successes that happen, so the number of failures has to be the total minus the number of successes. And then all of that's going to be multiplied by the combinations that can occur. Now the number of combinations, as we worked out over here, is known as NCR. So we just put in NCR. And what I will also acknowledge is that NCR can also be written as this. Or like this. Just be aware of all these different notations here, just in case they all can come up. But they all mean the same thing. And that's basically it. This is the main thing I wanted to get at with that example. Just this formula. Now we don't actually need to do any of these tree diagram stuff. I just did that now to demonstrate how this formula was made. But basically now all we can do is just use this formula and solve stuff, and we don't need to worry about like drawing it out too much. Unless they specifically ask for a proof, then you might have to. But otherwise, no. So let's do a question now. If I said it is a 1 in 5 chance. Now let's change the probability, sorry. Let's say it is a 3 in 7 chance I win a game of cards. If I play 10 games, what is the chance of me winning 6 games? What we can do now is we just sub in all of this information into the formula. So ultimately we should circle all the stuff. First of all, we have 3 over 7 here, and this is representing the probability of any single attempt. So probability is going to be labeled as P. So any single attempt at a game, it's a 3 in 7 chance. That's the probability of any single attempt. But then we've got to say, okay, what's the total number of games? And we can see that the total number is 10. I'm going to play 10 games. So we know that's going to be our total number, which is going to be n. Now we've got to think, okay, how many successes are happening? And as we can see here, the number of successes is 6. So we just put in that as R. So ultimately now, we can say that we have a binomial distribution right here. And we can say that if x is distributed binomially, now we also got to write down, before I get to that, I should probably, okay. We can basically say that x is distributed binomially. And now what we do is we write down two things: the number of games and the probability. So the number of games we're playing is 10. The probability is 3 over 7. So this is basically saying variable x is distributed binomially. We have 10 attempts and the probability is 3 over 7. I just want to quickly check that. Is that actually an notation? Yep, good. Now what we're saying is, okay, we need to find the probability of 3 successes happening. So that would be labeled as the probability that x equals 6. So this is basically saying the number of probabilities. And that's going to equal. Now we go to our formula, the probability that x equals r. So we see we have written that out. We know 6 is our r. We have p to the power of r, 1 minus p to the power of n minus r times ncr. Now conventionally speaking, they usually put ncr at the front. So I'm just going to move that here. It doesn't really matter, I've just changed the formula order. But it doesn't really matter. It's still ncr times p to the r times 1 minus p to the r. But now if we plug all this into the formula, ncr is going to be, we said n is 10, so 10c r, r is 6, and that's going to be times p to the r. So the probability is 3 over 7. That's going to be the chance of any one thing happening to the power of r, which is the number of successes. Now the number of successes is r, which is 6. And all of that times 1 minus p, so the probability of a failure to the power of the remaining attempts that need to be failures. So the probability of a failure is going to be 1 minus p, which is 1 minus 3 over 7, to the power of n minus r. So if we have 10 attempts and we have 6 successes, that means we have 10 minus 6 that have to be failed, which is 4. So probability of x equals 6, the probability that we have 6 successes is going to be 10c6 times 3 over 7 to the power of 6 times 1 minus 3 over 7, which is the same thing as 4 over 7 to the power of 4. Now what we can essentially do is put this in our calculator and solve it. So what I can do now is I can go run matrix, then go option. Now to get over here, 10c6, we go to option, go to calc. No, not calc, sorry, I meant start. Okay. No, it's prob. Okay, so we go option, then we go over here to prob ncr. So then I put over here, we are putting 10c6, so right in that order, 10c6, all of that times. Then we can basically just put the rest of the data in. 3 over 7, the power of 6 times first, 4 divided by 7, the power of 4. As you can see, I've just put it in, subbed it all in from here, and we get approximately 0.139. Now let's move on. Let's do another question. If I said y is distributed binomially, sorry, if that's question 1, let's say this is question 2, and I'm going to say this over here, and I'm going to find part A here. Find the probability that y is equal to, I'm going to change that, sorry, that should be 0.6, my bad. So let's say find the probability that y equals 10. What that means is what I've done now is I have not given a worded question. I've instead this time given just this notation, which is basically just a summary version of all this info. In this, what I've said is y is distributed binomially, 12 attempts, and the probability of each success being 0.6. So what I'm going to also do is I'm going to write down the notation over here as a summary. But if I said if x is distributed binomially, we have n and then p. That's the notation that we need to be familiar with. So what this is saying is x, the random variable x, is distributed over here binomially for the b, and then n and then p. Pretty self-explanatory for n and p. So what this is basically saying is y is a distribution that is distributed binomially, and we have 12 attempts, which is n, and then 0.6 for the p. Now I'm saying find y equals 10. Now, usually in this notation, as you may have recognized before, that is basically saying the number of successes. So we have 10 successes. So all we really need to do, just plug it in. So we know the probability that x equals r is ncr p to the r 1 minus p to the n minus r. So just sub that all in. And I think it's best to label what n, r, and p are. So as you can see, in a binomial, there's only really three things we need. N, p, and r. Here it's been given n, p, and r. Just remember where all of these things come in and the context of the question, and it's usually not too tricky to solve. And then all you got to do is you got to say, okay, the probability that y equals 10 is going to be ncr, so 12, because that's n, cr, which is 10. Then times p to the r, so probability 0.6 to the power of the number of successes, which is 10, times 1 minus p, so 1 minus 0.6 to the power of the remaining attempts, so n minus r. That's going to equal 12 c10, 0.6 to the 10. 1 minus 0.6 is 0.4. Now I forgot to write down n minus r. We said n was 12 and r was 10. So 12 minus 10, which is 2. Then after that, all you need to do, put that in the calculator. 12 c10, all of that times 0.6 power of 10 times 0.4 power of 2. That in, we get approximately 0.06385. 0.0639. There you go. Now what I'm going to do finally is one final part. If I now said find the probability that y is greater than 9, what that essentially means is that's saying find the probability that y is equal to 10, or, so when I say or, that means we have to add plus the probability of y is equal to 11, or plus the probability of y equal to 12. Now we know 12 is n, that's the maximum number of attempts. So that means we would just go up from all the numbers greater than 9 until we get up to the maximum, which is 12. And then basically we'll just sub all those in the calculator. Now I'm going to show in a later video that we can do all of this much, much quicker using a bit of a shortcut, but I'll show that in my next video. But for right now, I just want you to have a good understanding of what the formula means and why it's derived and how it came from and everything. And then once again, you would plug all this in the calculator and you'd get a number. But because that's mostly busy work, I'm not going to get too bogged down in that. Now, finally, if I said find the probability that y is less than or equal to 5, what that means is we're going to have the probability that y is equal to 0, so that means 0 successes, that's always the lowest amount, plus the probability that y equals 1, plus the probability that y equals 2 plus the probability that y equals 3 plus the probability that y equals 4, all the way up to the probability y equals 5. Because in this case, we're saying y is less than or equal to 5. So because of the or equal, we include 5. So I basically listed all the y values that would be 5 or less, all the way down till we get to the minimum, which is 0. Now similarly over here, as we can see, when I said probability y is greater than 9, that means we include everything greater than 9 up to the maximum, which is 10, 11, and 12. And then you can pretty much solve all of these, and you add them all up and get your answer. So that's going to conclude my coverage for this video. And in my next video, I'm going to cover a few more extensions of the binomial distribution and how you can do a lot of these kind of things much, much quicker using the calculator.